Thank you. Yeah, today, as introduced, I'm Flemming, and today I want to talk a little bit about our recent work on using convex optimization to quantify the limits of quantum control, and kind of how Julia played a unique role or uniquely useful role in bringing that to practice. So I know there's probably a few experts in the room, but to those that don't really know much about quantum control, let me try to introduce at least the idea as to why quantum control and the limits of the performance of quantum control matter in the world. So I think the easiest way to recognize that is to recognize that quantum control lies at the heart of a lot of quantum information technologies. So take, for example, quantum computing. One way to view a quantum computation is as a very carefully designed, deliberately controlled evolution of a quantum state. And as a consequence, the speed and accuracy with which we can control quantum states put a limit on the capabilities of these technologies. And if we want to evaluate those potentials adequately, it ought to be useful to study and quantify the limitations of quantum control. So that motivated us to build a convex optimization-based framework, specifically sum of squares programming-based framework, that allows us to put hard limits or compute hard limits for the performance of quantum control for a quite wide range of problems. So, and if you're familiar, those really extend, in a sense, the known quantum speed limits by incorporating in addition to fundamental physics, also technological constraints and system-specific information, because in practice, the last thing that we're really being limited by is fundamental physics. And also from a practical perspective, these bounds can be useful because they can serve as witnesses of fundamental limitations. They can certify optimality of heuristically derived control policies or control sequences, say obtained via local optimization or machine learning, or even flat out serve as performance targets. So here, what's shown here is an example of the type of problems that we wanted to look at, and that is a qubit in a cavity that is subjected to a continuous measurement setup, in this case homodyne detection. Then this is hooked up to a quantum filter that allows us to kind of get the state conditioned on our measurements, and then there's a feedback controller that actuates this qubit here to do what we want to do. And in this case, that's to kind of maximize the average fidelity, which means in this cartoon here, to have the state be as close as possible to the North Pole. And what we wanted to ask is, can we put a limit on how close we can keep this if all the stars align to the North Pole? Right. So on a more abstract level, we consider quantum systems that are described by the Belevkin or quantum filtering equation. So we do allow for continuous measurement, as in this example here. So to then enable feedback control, but if you like open loop control, that's no problem. You just drop the measurement, and then this equation just simplifies or degenerates to the familiar von Neumann or Louisville master equation. We also assume a quite prototypical actuated Hamiltonian form of our control system. And what I should mention also is that we allow for technological constraints such as bounds on the control drives with which we can actuate our system, or even more complicated constraints such as constraints on the state. Think of a limited amount of probability mass that can escape out of the logical subspace of a qubit, for example. We can constrain that as well. So in here again, in a formal setting, what we want to do is put a bound on what is the best possible performance that we can achieve, which is characterized by this optimal control problem. It actually turns out we can combine ideas from dynamic programming and convex optimization to do quite that. And the key insight that we leverage here is that the optimal control function, which is, of course, encodes the solution to this control problem and therefore is really hard to compute, is characterized as a infinite dimensional linear program, so a convex optimization problem. And what this convex optimization problem seeks to do is kind of find a smooth function which underestimates this value function everywhere and is as close as possible to the true value function at the initial time of the control problem, And of course, the value function encodes the optimal value of the control problem at its initial time. So therefore, you get by construction a lower bound. And the key thing is you can kind of do this without knowing what the actual value function is. So what is relevant here is that this is a convex problem, but it's infinite dimensional. So we can't actually solve it directly. What we take advantage of then is the nice structure of the quantum control problem. So we can apply the moment sum of squares hierarchy, and instead of looking for any smooth function that underestimates this value function, we can just look for a polynomial up to some fixed degree d to underestimate this value function. And actually, that turns out, using sum of squares techniques, to be equivalent to a semi-definite program. And that has several advantages. On the one hand, we have a range of semi-definite programming solvers available to solve these types of problems. And on the other hand, we not only get a bound on the control performance by solving these problems, but also we get, as a byproduct, a polynomial function that kind of looks and talks like a value function, because the idea is for it to approximate the value function well from below. And that can inform controller design, and I'll show you a manifestation of that later. Another nice thing is this is kind of by construction has a hierarchical structure. So that means I can just increase the degree of my polynomial and get a better bound. Of course, the problems then become harder and more expensive to solve, but at the end of the day, that is in practice desirable because I can trade off more computation for higher quality bounds. And you can even show under certain regularity conditions, this is consistent in the sense that you get arbitrarily good bounds in the limit. So how is Julia uniquely useful for this? I would say the main reason is it's really rich optimization ecosystem, which is perfectly suited for this kind of thing. In particular, sum of squares.jl deserves a lot of credit, which allows very easy setup of these sum of squares programs and then translates them automatically in the equivalent semi-definite programs, which then can be pushed to your solver of choice through the MathHub interface. So all we had to do is write kind of or expose a high-level interface that allows us to specify our control problems in a symbolic form on the back of these like nice symbolic modeling tools in Julia. And then all these bounding problems can be generated automatically without understanding much that's going on. So, and the last thing I want to show you is how that can be useful in practice. So here, I want to go back to this qubit example I showed in the beginning, where we want to compare two different measurement setups. So you can either do feedback with photon counting or homodyne detection, which are two different technologies. And you can compute the bounds on the best performance that you could expect from a controller using these measurement setups. And there's 3 points I want to make. The first one is, even for low degrees of this polynomial, you get non-trivial bounds. So the trivial bound here is 1. But even for low degrees, they are meaningfully removed from 1. And the second point I want to make is, as we go through the hierarchy of these bounding problems here, the bounds turn out to be extremely informative. In particular, we constructed a heuristic controller actually based on these approximate value functions, which achieves a fidelity of 77.5%. And this bound certifies that kind of God can't do better than 78.5%. And yeah, so that's, of course, a strong statement if you go to your boss and say, I have a good controller. And the last point I want to make is that this is actually kind of a computational proof that homodyne detection in this setup is strictly superior to photon counting, because we have a controller that achieves 77.5%, whereas photon counting, we can at best hope to do something like 68%. And yeah, with that, I'd like to thank you.
I think we have time for one question, maybe as we transition to the next speaker. Manuel, if you're here, you could start getting set up.
Yeah, I want to follow up on that one too, but I'm not. I'm just going to ask, you might have said this at the beginning, but how does this scale with like the dimensionality of the underlying system?
Not as well. I mean, it's tied to dynamic programming. So as such, it's really limited to smaller problems. I think the biggest one that we've done is like state preparation for 2-qubit systems.
Okay.
Yeah.
Okay. Is our next speaker here? Okay, please. We could do maybe one more question while we're getting set up. Oh, okay, follow up.
Did you try any other optimal control solvers for getting these fidelities, or just this method?
I mean, the point. First of all, this is closed loop, so like optimal. Actually, you can do this for local optimal control if you wanted to, like open loop stuff. And the point here is to just quantify or certify global optimality, and everything out there is just like, okay, I do like gradient-based optimization, which is like gives you no certificates on what you get. So no, because that wasn't really the point of this endeavor.
Well, I might have something that could to challenge your God on this one, so we could talk afterwards.
Okay.
Okay, thank you.